Welcome to another podcast. This episode we're going to be taking a look at the derivative as an operator. And this is in stark contrast to the way we've been looking at the derivative so far this semester, which is typically as a limit. So the way that we've understood the derivative is if you give me a function y equals f of x, then I can find the derivative f prime of x as a result of using the definition of the derivative, which as we've become aware of at this point is a hassle to do algebraically, but it's given by this particular limit. And for the rest of the semester, we don't want to have to repeat that exercise over and over and over again every time we find a derivative. So it would be in our best interest to think of the derivative as an operator and learn what the properties of that operation are. Specifically here, I want to talk about some of the different notations that we use with the derivative as an operator, and then we'll get into sort of what are the properties of that operator. So these are sort of forms of the derivative. Now, what's difficult about this is depending on what text you're reading, the text might contain very different forms from one text to the next. And the unfortunate thing about calculus is you need to be somewhat familiar with all of these forms depending on the context. So we're going to start with the assumption that y is a function of x. And so one notation is dy dx. So this literally means the derivative of y with respect to x. So let me go ahead and write that out. This is the derivative of y with respect to x. And so we know that x is the independent variable. And so one of the things you look at with this particular form is you're taking the derivative with respect to the independent variable, but the output is the dependent variable y. This is the exact same as saying df dx, because y is a function of x, and we call that function f. So saying df dx is the same as saying dy dx in this context. And both of these operations together, these are what are called the Leibniz notations, or Leibniz, depending on how you pronounce it. This is the Leibniz notation for the derivative. Now compare that with the prime notation for the derivative. So we might ask y prime. So this is the derivative of y. And the problem with this particular notation, even though we use it all the time, is unlike dy dx, I know I'm taking the derivative with respect to x. I know that's the independent variable. If I just write y prime, then I need some other bit of information to tell me what the prime is actually telling me to operate on. What's the independent variable here? Is it x, t, something else? So the best we can do at this point is that this means the derivative of y with respect to the independent variable. So whatever that variable is, that's what we're going to be taking the derivative with respect to. So you could also say y prime is equal to f prime of x, and notice how I put the prime on the f, not on the outside here. That's also okay notation. Some other notations that appear that are maybe a little bit less common are these big D operator notations. So if I asked what is the derivative with respect to x of the function y, that's the same as saying dy dx. Or I could ask what's the derivative with respect to x of the function f. That's the same thing as asking df dx. The prime notation is Newton's notation. So this is Newton's notation for the derivative. And we need to be comfortable with all of these definitions, all these notations and forms of the derivative, specifically because we're going to think of the derivative as an operator from now on, and these are operator notations. We're not going to involve the limit every time we want to do a problem. So the question is, what is an operator? And the derivative is an example of that, but to understand an operator, we have to think a little bit more about what the derivative does. And so the derivative is basically an operation which operates on an input and gives an output. And an operator takes the same input and transforms it into the same output. And what I mean by that is the inputs for this are functions. And not only that, they're functions of a variable. In this case, the variable is x. That's our independent variable. So I get an fx, and what comes out of them is another function called the derivative, which is the same. It's also a function of the same variable x. And so you can think of the derivative as an operator in the sense that it operates on the variable x, turning it into another function of the same variable. The fact that it keeps the same variable is important, and it differentiates it from something called a transform. So there's two big classes of operations in mathematics. There are operators, and then there are things called transforms. Operators maintain the same variable, while transforms will change the variable via the operation. And so we're not going to deal with transforms in this class, but in future math classes you may. I just wanted to simply talk about the fact that the derivative is an operator because it maintains the same independent variable in the problem. Now, the derivative is actually a linear operator. And the question is, what does that mean? So the derivative is a linear operator. First thing that means is it has the following property. The derivative with respect to x of a constant times a function is the constant times the derivative of the function. In other words, you can think of this as being the derivative distributes across, the word we use is scalars, but you can think of it as constant multipliers. So if you have a constant times a function, the derivative can pass over the constant and operate on just the function. Basically, you're distributing it across the scalar multiplication. The second property is that it distributes across addition exactly as we would expect it to. So this is df dx plus dg dx. It operates on each one individually. And finally, the third property here is that it also operates or distributes across subtraction, simply because if you look at this, this is the derivative with respect to x of the function f plus the derivative with respect to x of the function negative g. I'm thinking of these two as being added, not subtracted. So from property 2, I can distribute across addition. And then property 1 tells me I can take the derivative and pass it inside scalars, and the scalar here is negative 1. So I can think of this as having this property where the negative pops out, and I'm just taking the derivative of g. And so if you look at this, what we think of in this case is that the derivative distributes across addition and across subtraction. When an operator has all three of these properties, then we call it a linear operator in mathematics. And linear operators are some of the most important class of operations or operators that we use in all of mathematics, and the derivative is a great example of those. Alright, in future videos we're going to look at properties of the derivative related to the fact that it's an operator, and look at some specific operations such as the product rule, the quotient rule, etc. Alright, thank you for watching.